Hello, companion of this evening journey. Perhaps you're in a moment of pause when the mind naturally turns to deeper reflections about the world around us. There's something comforting about allowing thoughts to flow unhurriedly, like a serene stream finding its natural path through the landscape of consciousness, exploring conceptual territories that remain hidden during the daily rush of routine. I would like to invite you on an extraordinary voyage tonight. A journey that doesn't require you to move even a centimeter from where you are. It's a journey through the deepest reality we know, or think we know. It's about something that might be vibrating exactly where you are right now, something so small that it completely escapes our perception, but so fundamental that it could be the very essence of everything that exists. It's a story about invisible music, about hidden dimensions, about the possibility that our familiar reality is just a small fraction of something unimaginably more vast and strange. Have you ever wondered what you're really made of? I'm not referring just to the skin, muscles, and bones that form your physical body, nor even to the atoms that compose these familiar structures. I'm talking about something even deeper, more fundamental. Imagine for a moment that we could dive deeper and deeper into the matter that forms your body, passing through the microscopic cells that work tirelessly to keep you alive, then through the complex molecules that orchestrate the dance of life, then through atoms with their dense nuclei surrounded by moving electrons, and continuing this dizzying journey until we reach the smallest possible level of reality, the very heart of material existence. What would we find there, in that realm almost impossible to imagine, where the familiar laws of physics give way to phenomena that defy our most basic intuition? For decades, the brightest scientists in the world believed we would arrive at fundamental particles, small points without dimension, pure mathematical objects that would be the basic building blocks of all reality. But what if I told you there might be something even more fundamental? What if, at the heart of all matter and energy in the universe, there were not static points, but dynamic strings? Strings so minuscule they make an atom seem like a giant planet, vibrating at specific frequencies that determine everything, from the mass of particles to the forces that keep the cosmos united in its eternal dance? This is the audacious and almost poetic proposal of string theory, one of the most elegant and controversial ideas in modern physics. It whispers to us a fascinating and transformative possibility that the entire cosmic symphony, from the rhythmic beating of your heart to the majestic birth of distant stars, from the delicate floating of a leaf to the imposing rotation of entire galaxies, might be at its deepest essence music. Music made by invisible strings, dancing in dimensions our mind can barely conceive, creating harmonies that manifest as the very reality we experience. There's something deeply comforting about this idea, don't you think? The possibility that, beneath all the apparent solidity and separation of the physical world, there exists a fundamental unity, a cosmic music of which we are all part. That you and I, the distant stars, the deep oceans, even the thoughts flowing in your mind at this moment are all different expressions of the same universal symphony, notes in an infinite composition that the universe is constantly creating and recreating. Can you hear the silence around you right now? That silence that seems empty on the surface, but actually teems with invisible and constant activity. Every cubic centimeter of space beside you is filled with a microscopic dance so intense and frenetic as the traffic of a great metropolis during rush hour, but silent as the softest whisper of wind among the leaves of an ancient tree. To begin truly understanding string theory in all its magnificence, we must first dive deeply into the quantum world, that strange and wonderful realm where the familiar rules of our daily life simply don't apply, where common logic dissolves like salt in water. It's as if nature had developed two completely different personalities over billions of years, one we know well and trust, made of solid objects and predictable behaviors that obey the laws of common sense, and another, microscopic and elusive, where things can literally be in two places at the same time, where particles appear and disappear like ethereal ghosts, and where conscious observation itself fundamentally changes the observed reality. Imagine you're looking at your hand right at this moment. It seems solid, substantial, real, doesn't it? You can feel its texture, its temperature, its weight. But if we could somehow magnify your vision trillions and trillions of times, you would discover something that might shock your perception of reality. Your hand is almost completely empty. The atoms that form your skin, muscles, and bones are like tiny microscopic solar systems with minuscule, dense nuclei surrounded by electrons dancing in probabilistic orbits, regions of space where they probably are, but never with absolute certainty. And between these atoms, much empty space, proportionally emptier than the space between stars. But this void is actually a stage for one of the most extraordinary and complex spectacles in nature. Subatomic particles constantly appear and disappear in this quantum theater, emerging from apparent nothingness and returning to nothingness in fractions of seconds so small they defy our most basic capacity for imagination. It's as if the universe were a calm and serene ocean on the surface, but with turbulent, complex, and invisible underwater currents moving enormous amounts of energy and information in patterns we're only beginning to understand. Throughout the entire 20th century, an era of unprecedented scientific discoveries, physicists discovered a true zoo of subatomic particles, each with their own peculiar and fascinating characteristics. There were quarks with deliciously poetic names like charm, strange, enchantment, and beauty that combine in specific and elegant ways to form protons and neutrons, the building blocks of atomic nuclei. There were leptons, a family that included the familiar electrons orbiting atomic nuclei and the mysterious neutrinos, particles so elusive and ghost-like that trillions of them pass through your body at this exact moment without you feeling absolutely anything, as if you were completely transparent to them. And there was something more equally fascinating, particles that carry the fundamental forces of the universe. Photons, massless particles that transport light and all electromagnetic radiation, from radio waves to the most energetic gamma rays. The W and Z bosons, discovered in heroic experiments, responsible for the weak nuclear force that governs certain types of radioactive decay. Gluons, particles that hold quarks together with a force so incredible that the more you try to separate them, the stronger the attraction between them becomes. It was like discovering that nature possessed a secret and sophisticated alphabet, and each particle was a letter in this cosmic alphabet, capable of combining with other letters to write the poetry of existence. But something deeply troubled the most perspicacious physicists. Have you ever wondered why these specific particles exist, and not completely different ones? Why does an electron have exactly the mass it has, not a little more or a little less? Why are there precisely 4 fundamental forces in nature? Gravity, electromagnetism, strong nuclear force, and weak nuclear force, and not 3 or 5 or 10 or any other number? Why do nature's constants have the exact values they have? These questions began to form a symphony of mysteries that cried out for a deeper and more unifying explanation. There are moments in the history of science, rare and precious moments, when we encounter a paradox so deep and fundamental that it shakes the very foundations of our understanding of reality. Imagine 2 incredibly intelligent people, each speaking a completely different language, each language perfect and eloquent for describing its own particular world, but completely incapable of translating to one another, as if they were codes from different alien civilizations. This is exactly the extraordinary and frustrating dilemma that dominated physics for almost an entire century, challenging the brightest minds of humanity. On one side of this great conceptual divide, we have quantum mechanics, that absolutely extraordinary and almost magical theory that describes the world of subatomic particles with precision so impressive it becomes almost supernatural. Quantum mechanics allowed us to create practically all modern technology that defines our civilization. Computers that fit in the palm of your hand but are more powerful than supercomputers from past decades. Lasers that can perform delicate surgery or cut metals with microscopic precision. Magnetic resonance devices that let us see inside the living human body without causing any harm. And countless other technological marvels that our grandparents would consider pure magic. Quantum mechanics reveals to us that, at the most fundamental level of reality, everything is made of fluctuating probabilities, ethereal waves of possibility that materialize into concrete reality only when observed by a consciousness. as if the universe were a dream that becomes real only when someone is awake to dream it. On the other side of this conceptual abyss, we have Einstein's general relativity, an equally magnificent and poetically beautiful theory that describes gravity and the behavior of the universe on large scales with mathematical elegance that makes physicists sigh in pure admiration. It showed us revolutionary truths, that space and time are not fixed and immutable stages where cosmic events unfold, but dynamic actors in the cosmic drama, capable of curving like rubber, stretching like elastic, and rippling like the surface of a lake disturbed by a thrown stone. Thanks to general relativity, we can understand phenomena that seemed completely impossible. Black holes where time practically stops, the accelerated expansion of the universe itself, and even use GPS systems with millimeter precision because, yes, your cell phone needs to take relativistic effects into account to function correctly, compensating for the fact that orbiting satellites experience time slightly differently than we do here on Earth's surface. Both theories are incredibly, spectacularly successful in their own specific domains. Quantum mechanics predicts the behavior of subatomic particles with precision that frequently reaches more than 10 decimal places, a precision so extraordinary it would be like predicting the position of a grain of sand on a beach with an error smaller than the diameter of an atom. General relativity predicts cosmic phenomena, from planetary motion to the bending of light by massive objects, with mathematical elegance and observational precision that continue to impress scientists more than a century after its original formulation. But here lies the fundamental problem, the mystery that keeps physicists awake at night. These two theories, both extraordinarily successful, are fundamentally, irreconcilably incompatible when applied simultaneously to the same physical phenomena. It's as if nature spoke two completely different languages depending on the scale at which we observe it, one language for the very small, another for the very large. When we try to apply both theories at the same time, in situations where both quantum effects and gravity are equally important, the mathematical equations literally explode, producing infinite and completely meaningless results, as if mathematics itself lost its sanity. You might be thinking, rightfully, well, but when would this really be a practical problem? The answer is deeply intriguing, in some of the most crucial and fundamental moments in cosmic history. At the center of a black hole, where space-time curvature becomes extreme, but the physical dimensions involved are microscopic, simultaneously requiring both relativity and quantum mechanics. In the first moments after the Big Bang, when the entire observable universe was compressed into a volume smaller than an atom, but contained all the matter and energy that today spreads across billions of light years. In any situation where gravity becomes so intense that its fundamental quantum effects simply cannot be ignored. It's precisely in these crucial moments that current physics simply raises its hands in surrender and humbly admits, we don't know. It's an admission that is simultaneously humble and deeply frustrating for scientific minds, who have dedicated their entire lives to understanding nature. How can it be possible that nature, in its infinite wisdom, uses two sets of rules so dramatically different? Surely, at the deepest root of reality, there must be a single unifying theory, a universal cosmic language that describes everything harmoniously, from the smallest subatomic particles to the largest galactic structures. Have you ever felt lost trying to reconcile two apparently contradictory truths in your own life? Perhaps two different perspectives on the same event, or two conflicting ways of understanding a complex situation. Theoretical physics faced exactly this existential dilemma, but on a truly cosmic scale, with implications for our fundamental understanding of the very nature of reality. It was the year 1968, a time of cultural revolution and scientific discoveries, and a brilliant and determined young Italian physicist named Gabriele Veneziano was heroically struggling with a seemingly impossible problem to solve. He devoted days and nights trying to understand the strong nuclear force, that absolutely mysterious and powerful force that keeps protons and neutrons firmly united in the atomic nucleus, vigorously resisting the intense electromagnetic repulsion that should, by all rights of classical physics, make them fly away from each other in all directions like cosmic fireworks. The problem was that all conventional approaches failed miserably. The equations became intractable, calculations produced meaningless results, and the nature of the strong nuclear force remained shrouded in mystery like a physical sphinx. Veneziano was desperate for a new perspective, a new way to approach this fundamental enigma. It was then that fate intervened in an almost poetic way. Veneziano was leafing through an old, dusty mathematics book when he came across a formula apparently forgotten by time, created more than 200 years earlier by an extraordinarily prolific Swiss mathematician named Leonhard Euler. The formula, known as Euler's beta function, described abstract mathematical properties of one-dimensional objects, essentially mathematical strings. Something in that ancient and apparently irrelevant mathematics captured Veneziano's imagination in a way he couldn't completely explain himself. With the mysterious intuition that sometimes guides great scientific discoveries, that inexplicable feeling that something important is about to be revealed, he began to imagine a revolutionary possibility. What if fundamental particles weren't points without dimension, as all physicists had automatically assumed for decades, but tiny, vibrating strings? Have you ever had one of those extraordinary moments when an apparently crazy idea suddenly makes deep and almost magical sense? When pieces of a puzzle that seemed completely disconnected suddenly fit together perfectly, revealing a beautiful and unexpected pattern? Veneziano began calculating feverishly, applying Euler's ancient mathematics to the modern problem of the strong nuclear force, and what he discovered was absolutely extraordinary and transformative. If subatomic particles were really small vibrating strings instead of geometric points, many of the most thorny and persistent problems in particle physics would resolve naturally, almost as if nature itself had been waiting patiently for someone to ask the right question. It was as if a long-lost key had finally found its specific lock, unlocking secrets that had remained hidden for generations. But there was something even more surprising and potentially revolutionary hidden in these elegant equations. When other brilliant physicists around the world began systematically exploring the profound implications of Veneziano's apparently simple idea, they discovered something completely unexpected and challenging lurking in the depths of the mathematics. The theory simply didn't work mathematically in our familiar universe of three spatial dimensions. To be mathematically consistent and free of contradictions, to produce finite and sensible results, it inexorably required more dimensions. Much more dimensions than the three we experience directly. Initially, this discovery seemed like the premature end of the line for this promising idea. After all, we clearly live in a three-dimensional world, don't we? Up and down, left and right, forward and backward. These are the three familiar directions of space we've known intimately since birth, that our bodies navigate intuitively, that our minds understand effortlessly. How could a physical theory possibly require additional spatial dimensions that we simply don't observe in everyday reality? But then the most creative and visionary physicists remembered an old and almost forgotten idea, an audacious proposal made decades earlier by a German mathematician named Theodor Kaluza and later developed and refined by Swedish physicist Oscar Klein. This pair of thinkers had proposed a fascinating and counterintuitive possibility. What if these extra dimensions really existed, but were so small, so tightly compacted upon themselves, so intimately rolled up, that we couldn't perceive them directly with our limited senses or even with our most sophisticated instruments? Imagine a common garden hose viewed from a very great distance. To you, observing from afar, it appears completely one-dimensional, just a thin line with no perceptible width. But if you gradually approach, if you begin examining this hose with more and more detail, you'll discover that it actually has substantial width and thickness. It's genuinely three-dimensional, with a rich internal structure that was simply invisible at a distance. Kaluza and Klein proposed that our entire universe could be exactly like this metaphorical hose, apparently three-dimensional when observed at familiar scales, but possessing richly structured extra dimensions that are hidden at scales so small they completely escape our direct perception. The nascent string theory embraced this radical idea with almost religious enthusiasm. Not only did it graciously accept the probable existence of extra dimensions, but it made them absolutely fundamental to its mathematical functioning. And the more physicists patiently explored this extraordinary possibility, the more deeply they dove into the mathematical and physical implications, the more wonderful and poetically beautiful it became, revealing layers upon layers of elegance and hidden meaning. Close your eyes for a moment, if you feel comfortable doing so, and imagine the pure and crystalline sound of a violin played by a skilled musician, that sweet and penetrating note that seems to float in the air like a sound butterfly, that vibrates not just in your ears but throughout your entire being, touching something deep in your soul. You know intuitively that this extraordinarily beautiful sound is created by the delicate vibration of a string, a physical string that, when touched with precision and sensitivity, produces complex sound waves that travel through the air to your ears and magically transform into pure music in your conscious mind. Now expand this poetic image and imagine that all reality, literally everything that exists, is like an infinitely complex and beautiful cosmic orchestra, where countless trillions of microscopic strings, each smaller than anything you can imagine, constantly vibrate at different and specific frequencies. Each unique vibration frequency, each distinct harmonic pattern, would correspond to a different particle in the subatomic zoo that physicists discovered throughout the past century. The slowest and deepest vibration could manifest as an electron with its specific charge and characteristic mass. A slightly higher and more energetic frequency could materialize as one of the quarks that form protons and neutrons. An even faster and more intense vibration could appear as a photon, a particle of pure light traveling at the universal maximum speed. It's as if the entire universe were an infinitely complex and beautiful symphony, and each subatomic particle were an individual note in this cosmic composition that never stops playing. This is the poetically beautiful essence of string theory, the profoundly musical idea that, at the most fundamental imaginable scale, approximately 10 to 35 meters, a size so incomprehensibly small that it relates to a proton as a proton relates to you, as you relate to a galaxy, there exists something that vibrates perpetually. Not solid atoms, not structureless point particles, but minuscule strings in perpetual state of harmonic vibration, dancing eternally in the most intimate spaces of reality. Think for a moment about the fundamental difference between the keys of a well-tuned piano. Each key produces a completely different and recognizable note because it corresponds to an internal string of specific size and tension. In the longest and thickest strings, located at the base extremes of the instrument, the vibration is slower and the produced sound is deeper and more profound. In the thinner and shorter strings, situated in the treble regions, the vibration is much faster and the resulting sound is more acute and brilliant. In string theory, something philosophically similar and mathematically elegant happens. The same fundamental string, the same basic physical entity, vibrating at different specific frequencies or distinct harmonic modes, manifests as completely different particles with unique properties and characteristics. But there's a crucial and fascinating difference between the familiar strings of a violin or piano and the hypothetical strings of string theory. Musical strings we know vibrate in common air, in our familiar and comfortable three-dimensional space, producing sound waves that our ears evolved to detect and our minds to interpret as music. String theory strings, on the other hand, vibrate in multidimensional space-time, an exotic mathematical realm that might have 10 or 11 complete dimensions, depending on the specific version of the theory we're considering. Can you even begin to imagine this? It's an almost impossible challenge for our minds, like trying to visualize a color that never existed, or hear a sound beyond the physical capacity of our ears, or touch a texture that completely transcends our sensory experience. Our minds and brains evolved over millions of years to competently navigate three familiar spatial dimensions. So, extra dimensions are almost impossible to visualize directly or understand intuitively. But mathematically, surprisingly, they emerge naturally from string theory equations, as if nature itself demanded this expanded and rich space to express all its fundamental complexity and inherent beauty. And here's one of the most extraordinarily beautiful and poetically satisfying parts of the theory. These fundamental strings don't vibrate randomly, like loose strings in the wind. Instead, they vibrate in specific and precise mathematical patterns. in carefully structured cosmic harmonies that absolutely determine all observable properties of particles. We detect in our most sophisticated laboratories the exact mass of an electron, the precise electric charge of a proton, the specific intensity of electromagnetic force, the speed of light in vacuum. Literally all of this could be a direct and inevitable consequence of the sublimely complex music that these microscopic strings play eternally in the quantum void on this multidimensional stage that sustains all reality. There's something deeply moving and almost spiritual about this perspective. Have you ever wondered why music moves us so deeply? Why a specific melody can make us cry, or fill us with inexplicable joy, or instantly transport us to distant memories? Perhaps it's because at some deep and unconscious level of our existence, we recognize in music a distant but true echo of the fundamental harmony that might be constantly playing at the heart of reality itself. Perhaps we're literally made of music. Music as ancient as the universe, as fundamental as existence itself, as beautiful as any symphony ever composed by human mind. Tonight, before finally surrendering to restorative sleep, do a fascinating and revealing thought experiment with me. Imagine you're a tiny ant living exclusively on the perfectly flat surface of a sheet of paper. For you, a two-dimensional ant, the entire universe would be completely flat and limited to the two dimensions you can explore directly. You could move forward and backward along one direction, left and right along a perpendicular direction. But the concept of up or down would be literally unthinkable, as alien to your experience as a fourth spatial dimension is to us. Your reality would be genuinely two-dimensional, and nothing in your direct experience would suggest the existence of a third dimension. Now imagine that a three-dimensional being, perhaps a human observing from above, took that sheet that constitutes your entire universe and delicately rolled it into a perfect cylinder. For you, small ant walking on the surface, absolutely nothing would change in your everyday experience. You would still experience only two navigable dimensions, still could move in the same familiar directions, still live in an apparently flat universe from your limited point of view. But in the greater reality, invisible to you, your sheet universe would now possess a genuine third dimension, rolled in such a subtle way that you would never perceive it directly, even crawling tirelessly throughout your entire life over this curved surface in ways that completely transcend your capacity for perception. This apparently simple but profoundly revealing analogy helps us begin to understand one of the most revolutionary and transformative ideas of string theory: the extraordinary possibility that our familiar universe might possess additional spatial dimensions that are rolled so tightly upon themselves, compacted so intimately at microscopic scales, that they remain completely invisible to us, creatures limited to the three spatial dimensions we know and in which our conscious experience unfolds. But how many extra dimensions could exist in this hidden cosmos? The first historical versions of string theory, developed by courageous pioneers in the 1970s and 1980s, suggested the existence of 5 or 6 additional dimensions beyond the familiar 3. More sophisticated and mathematically refined versions, developed by subsequent generations of brilliant theoretical physicists, propose even more impressive numbers, up to 7 complete extra dimensions, totaling 10 or even 11 dimensions in the complete and true universe. It's a number that literally makes the mind spin in conceptual vertigo, isn't it? Try for a moment to imagine not just a fourth spatial dimension, but a fifth, a sixth, a seventh, each as real and fundamental as length, width, and height, but completely hidden from our direct perception. And how would these extra dimensions be rolled up or compacted in the fabric of space-time? Here, string theory presents us with a truly impressive gallery of mathematical possibilities, as beautiful as unimaginably complex. These dimensions could be rolled into exotic and elegant geometric forms with names that sound almost poetic. Calabi-Yau manifolds, mathematical structures of symmetry so intricate and sophisticated they seem like abstract sculptures created by a cosmic artist of infinite genius. Geometries that exist in 6-dimensional spaces and possess mathematical properties so special that only a few hundred examples are known to the world's most specialized mathematicians. Imagine trying to meticulously explain the 3-dimensional form of a perfectly bloomed rose to someone born completely blind who never had any visual experience. You could patiently describe the delicate and soft petals, the firm green stem, the sharp thorns, the velvety texture, the sweet and penetrating perfume. But you could never completely transmit the integrated visual experience of its multifaceted beauty. Similarly, these multidimensional geometric forms exist in a pure mathematical realm that our limited spatial intuition simply cannot reach directly, no matter how desperately we try to visualize them. But here's perhaps the most fascinating and philosophically profound aspect: the exact geometric way these extra dimensions are rolled and organized could literally determine everything about the fundamental laws of physics in our apparent three-dimensional universe. It's as if nature were an infinitely sophisticated cosmic origami, where the precise way multidimensional paper is folded, curved, and compacted completely determines what kinds of subatomic particles and fundamental forces we observe in our limited perceptible reality. Different specific forms of dimensional compactification could, in principle, produce universes with completely different and possibly unrecognizable physical laws. In some alternative universes, stable atoms might not be able to exist, making chemistry and life impossible. In others, gravity might be a repulsive force instead of attractive, preventing the formation of stars, planets, and galaxies. Or perhaps there could be literally dozens of different types of electrons, each with distinct mass, charge, and magnetic properties, creating a periodic table of unimaginable complexity. Perhaps 5 or 6 fundamental forces could exist instead of the 4 we know, or maybe just 2, creating a universe of elegant but limited simplicity. Have you ever contemplated the dizzying possibility that perhaps infinite versions of reality exist, each corresponding to a geometrically different way of folding these invisible extra dimensions? And that we simply had the extraordinary cosmic luck, or perhaps anthropic inevitability, of being born in a specific version where physical laws permitted not just the formation of complex structures like stars and planets, but also the emergence of life, consciousness, intelligence, scientific curiosity, and the capacity to contemplate our own existence and question the fundamental nature of reality. It's a perspective that simultaneously humbles us with our apparent cosmic insignificance and elevates us with the realization that we are natural products of universal laws operating at scales and complexities we're only beginning to understand. We are, in a certain sense, ways by which the universe developed the capacity to know itself, to question its own nature, to seek understanding of the deep principles that govern its existence and evolution. And if all this is true, if we really inhabit a multidimensional cosmos of unimaginable richness, then every breath you take at this moment, every thought flowing in your mind, every beat of your heart, is happening not just in familiar three-dimensional space, but immersed in an ocean of hidden dimensions, bathed by geometries our imagination can barely touch, part of a cosmic symphony whose complete score might be written in mathematical language of transcendent beauty. There's an almost mystical and transcendent beauty in the way string theory approaches some of the most thorny and apparently intractable problems of modern physics. It's like watching a master diplomat resolve a complex international conflict, not through force or coercion, but through deep understanding, infinite patience, and a broader perspective that allows all parties to find harmony where before there was only irreconcilable conflict. Remember the fundamental dilemma we discussed earlier. The seemingly irresolvable incompatibility between quantum mechanics and Einstein's general relativity? Two extraordinarily successful theories, each supreme in its own domain, but incapable of peacefully coexisting when applied simultaneously to the same physical phenomena. String theory doesn't force an artificial solution or impose reconciliation through brute mathematical manipulation. Instead, it offers a natural, organic resolution, almost as if the universe had been waiting patiently for decades for us to discover its secret and most fundamental language. When theoretical physicists heroically tried to combine gravity and quantum mechanics using the traditional model of point, particles, objects without spatial dimension, pure geometric points floating in the quantum void, invariably problematic and destructive mathematical infinities arose. Numbers without physical meaning that made calculations not just difficult, but literally impossible to interpret. It was like trying to sum an infinite series of increasingly large numbers without having any organizational method to control them or give them meaning. The results were equations that produced infinity as an answer to questions about physical quantities we know to be finite in reality, like the mass of a particle or the intensity of a force. But something truly magical and unexpected happens when we replace these problematic points with extended strings. Strings possess genuine spatial extension. However minuscule, they're not dimensionless points, but one-dimensional objects with real length and internal structure. And this apparently insignificant extension, this apparently trivial difference between a point and a line, changes absolutely everything about the underlying mathematics. It's like the difference between trying to perfectly balance a pencil on its tip, an impossible task due to inherent instability, and balancing it lying down, something perfectly stable and natural. In string theory, these problematic mathematical infinities that plagued generations of theoretical physicists cancel naturally through an almost miraculous mechanism of self-regulation. Contributions from different vibration modes of the string, the different ways a string can oscillate and vibrate, balance in a mathematically elegant and physically sensible way, producing finite, calculable, and interpretable results. It's as if nature had incorporated its own sophisticated quality control system, automatically preventing mathematics from becoming wild, uncontrolled, and physically meaningless. But there's something even more profoundly elegant and philosophically satisfying in string theory. Gravity is not an additional force that needs to be artificially grafted into the mathematical model. Instead, it emerges naturally, inevitably, organically from the intrinsic vibrations of fundamental strings. One of the specific ways a string can vibrate, one of the normal oscillation modes available to it, automatically produces a particle with all the exact properties that physicists associate with the hypothetical graviton, the particle that should carry gravitational force if gravity were quantized like the other fundamental forces. It's a discovery of surprising elegance, like discovering that the same mathematical equation that perfectly describes the complex waves of the ocean also, completely unexpectedly and without any artificial adjustment, describes with equal precision the graceful flight of birds. Gravity, that absolutely mysterious and fundamental force that keeps your feet firmly planted on the ground and keeps Earth in its stable orbit around the sun, that governs the dance of galaxies and the curvature of space-time itself, would simply be another note in the cosmic symphony of vibrating strings, neither more nor less fundamental than any other force in nature. And the implications extend even more deeply. String theory suggests an even more comprehensive and poetically satisfying unification. Not only would it promise to harmoniously reunite quantum mechanics and general relativity, finally overcoming the great conceptual divide that fragmented physics for almost a century, but it would also potentially unite all known fundamental forces of nature in a single unified mathematical description. Electromagnetism, strong nuclear force, weak nuclear force, gravity. All these apparently distinct forces would be revealed as different manifestations of the same fundamental vibration patterns, like different instruments in an orchestra playing different parts of the same universal composition. Imagine the philosophical revelation of discovering that all human languages, English, Mandarin, Arabic, Portuguese, Hindi, Swahili, are actually regional dialects of a single lost universal language, a primordial language from which all others emerged and to which all can, in principle, be perfectly translated. String theory proposes something conceptually similar for physics, that all forces and particles we observe in our most sophisticated laboratories are specialized dialects of a single fundamental cosmic language, spoken perpetually by vibrating strings in dimensions our imagination can barely touch. Have you ever experienced that sudden and unforgettable moment of crystal clarity, when something extraordinarily complex suddenly makes perfect and complete sense? When all the confusing pieces of an apparently impossible puzzle fit together simultaneously, revealing an image of beauty and order that was there all along, waiting patiently to be discovered. For many theoretical physicists around the world, string theory offers exactly that sensation on a truly cosmic scale, the tantalizing promise that the apparently bewildering complexity of the universe can emerge gracefully from surprisingly simple, elegant, and mathematically beautiful principles. principles that unify all physics in a single coherent vision of reality. Here's a question that might make your mind reel in conceptual vertigo and your sense of reality tremble at its foundations. What if our entire universe, with its hundreds of billions of galaxies, its countless trillions of stars, its rocky and gaseous planets, its complex life and emergent consciousness, were just a microscopic bubble floating in a truly infinite ocean of alternative universes? What if, at this exact moment as you read these words, there existed literally countless parallel realities, each with its own distinctive physical laws, its own unique cosmic histories, its own versions of matter and energy, life and death, consciousness and dream? String theory, especially in its most advanced and mathematically sophisticated versions developed in recent decades, not only allows this dizzying possibility, it almost requires it as a natural consequence of its internal mathematical structure. And this arises in a fascinating and philosophically disturbing way that challenges our most basic notions about uniqueness and reality. Remember the extra dimensions we explored in detail in previous chapters? Those hidden dimensions rolled so tightly upon themselves that they remain invisible to our direct perception? Well, it turns out there's a truly astronomical number of different ways these dimensions can be geometrically compacted and organized. Some of the most brilliant mathematical physicists in the world estimate there might be, approximately 1/500, geometrically distinct ways to roll and compact dimensions into stable mathematical configurations. To put this number in a perspective that might cause existential vertigo, this number is incomparably, unimaginably larger than the total number of atoms in the entire observable universe, including every star, every planet, every grain of cosmic dust in all the galaxies our most powerful telescopes can detect. Each one of these different geometric forms of dimensional compactification would produce, as an inevitable mathematical consequence, a universe with subtly or dramatically different physical laws from ours. In some alternative universes, electrons could be significantly heavier or lighter, fundamentally altering chemistry and making the complex organic molecules that form the basis of life as we know it impossible. In other universes, the gravitational constant could be 1,000 times greater or smaller, creating cosmos where stars could never form or where they would instantly collapse into black holes. Some universes could have 5 or 6 fundamental forces instead of our familiar 4, creating physics of unimaginable richness. Others could have completely different types of subatomic particles, chemical elements that don't exist in our periodic table, forms of matter and energy our current science doesn't even have language to describe. This truly vast and almost incomprehensible collection of universe possibilities is poetically called the string landscape, a metaphor that attempts to capture the immensity of a concept that defies our capacity for quantitative comprehension. Imagine a geographic landscape with 10,500 distinct valleys, each valley representing a possible universe with its own unique physical characteristics. We inhabit one of these specific valleys, but there are hundreds of trillions of trillions of trillions. Continue mentally adding trillions for several consecutive minutes of other possible valleys, each representing an alternative reality that could, in principle, exist and sustain its own exotic forms of structure, complexity, and perhaps even conscious life. But this almost infinite possibility of universes raises a profoundly intriguing philosophical and scientific question. Why do we inhabit specifically this particular universe, with these specific and well-calibrated physical laws? Why do nature's fundamental constants, the speed of light, Planck's constant, the electron's charge, the intensity of the strong nuclear force, have exactly the precise numerical values they have? Values that apparently by extraordinary coincidence permit the formation of stable atoms, lasting stars, rocky planets, complex organic chemistry, and eventually life, intelligence, and consciousness? One possible answer, but philosophically controversial, is what physicists and philosophers call the anthropic principle. The idea is simultaneously simple and deeply disturbing. We observe this specific universe with its particular physical laws, precisely because we're capable of observing it. In alternative universes where physical laws wouldn't permit the formation of complex structures like stable atoms, organic molecules, stable planetary systems, and carbon-based life, There simply wouldn't be conscious observers to question why things are exactly as they are. It's an observational selection argument. We can only find ourselves in universes that permit our existence. It's as if you were a solitary reader in an infinite library containing infinite books written in infinite languages. You would naturally find yourself reading one of the relatively few books written in a language you understand perfectly. Not because these specific books are special or privileged in some objective cosmic sense, but simply because they're the only ones you have the cognitive and linguistic capacity to read and understand. Similarly, we find ourselves in this specific universe not because it's objectively special, but because it's one of the few types of universe where observers like us can emerge and ask questions about their own existence. But there's an even more radical and philosophically vertiginous interpretation of this cosmic landscape. What if all these possible universes weren't just mathematical abstractions or theoretical possibilities, but literal descriptions of an infinitely rich multiversal reality that actually exists in all its incomprehensible magnificence? What if the string landscape weren't just a useful catalog of mathematical possibilities for theoretical physicists to study, but a literal and precise description of a multidimensional reality where each geometric possibility corresponds to a genuine, real, and physically existing universe? In this truly epic cosmological vision, there would be literally countless parallel universes coexisting in some deep mathematical sense. The vast majority of them completely sterile, without shining stars, without interesting planets, without organic chemistry, without life in any recognizable form. But in a small fraction of them, a fraction so small it defies our imagination but still representing an infinite number in absolute terms, conditions would be adequate for the emergence of complexity. Stable atoms, organic molecules, planetary systems, biological evolution. And in an even smaller fraction of this already tiny fraction, conscious life could arise, develop, evolve, question its own existence, develop science and philosophy choices, living an alternative life, exploring paths you didn't take in this reality. In the string landscape, this apparently fantastic speculation isn't just science fiction or philosophical daydreaming. It's a serious mathematical possibility that some of the brightest and most respected physicists in the world take seriously and study with the most sophisticated tools of modern theoretical physics. Not every scientific story is a triumphant and linear march toward absolute truth. Sometimes, frequently in fact, the most revolutionary and potentially transformative ideas face fierce resistance, legitimate intellectual skepticism, and passionate debates that extend for decades or even centuries, dividing entire scientific communities and creating controversies that transcend academia to influence broader culture. String theory, despite all its undeniable mathematical elegance and inspiring conceptual power, is by no means an exception to this historical pattern of resistance and debate. Imagine you're watching an intense philosophical and scientific debate between two groups of extraordinarily brilliant thinkers, each group composed of some of the sharpest minds of our era. On one side of the great intellectual auditorium stand the passionate string enthusiasts, theoretical physicists who see in the theory the long-sought key to physics' holy grail, a truly unified theory of everything, a single and comprehensive mathematical description that would explain all natural phenomena, from the behavior of individual quarks to the evolution of entire galaxies. On the other side, equally passionate and articulate, stand the systematic skeptics, physicists equally intelligent, equally dedicated to the pursuit of scientific truth, but deeply concerned with the epistemological implications of string theory for the traditional scientific method and for our understanding of what constitutes valid scientific knowledge. The most prominent and articulate critic is a respected and prolific physicist named Lee Smolin, who wrote a provocative and influential book titled The Trouble with Physics. Smolin, who is by no means a marginal scientist or reflexive contrarian, but a serious researcher with important contributions to theoretical physics, argues carefully and precisely that string theory, for all its undeniable mathematical beauty and aesthetic appeal, suffers from a potentially fatal flaw. It might be, in principle and forever, impossible to test experimentally in any meaningful way. This is a devastating accusation in the context of Western scientific tradition, which developed over centuries based on an elegant and self-correcting process. Theories are proposed based on observations and intuitions. Their observable consequences are deduced through rigorous mathematics, and then careful and controlled experiments are made to verify whether these theoretical predictions are correct or incorrect. It's like a continuous and productive dialogue between the creative human mind and the objective universe, where we ask specific and articulated questions through experiments, and nature responds with verifiable and reproducible facts that confirm or refute our ideas. But string theory, critics argue with legitimate concern, operates at scales of energy and size so extreme and inaccessible they might be forever beyond the reach of any conceivable experimental investigation. Fundamental strings are so incomprehensibly small that investigating them directly would require particle accelerators with energies trillions of times greater than anything we can build. Machines the size of the entire solar system or perhaps the galaxy. Extra dimensions, if they really exist, are compacted so tightly and at such microscopic scales that their signatures might be impossible to detect with any imaginable technology, not just with our current technology, but with any technology that the laws of physics permit in principle. This creates a deep and potentially destructive philosophical dilemma for the theory. Can a proposition be legitimately considered scientific if it cannot, not even in theoretical principle, be tested experimentally? Or would we be inadvertently entering the realm of pure mathematics, speculative philosophy, or even metaphysics, respectable and important intellectual domains, but fundamentally different from traditional empirical science? Peter Voigt, another vocal and mathematically sophisticated critic, goes even further in his devastating analysis. He argues that string theory is not only experimentally untestable, but is not even wrong, a reference to a famous and cutting phrase by physicist Wolfgang Pauli, who used this expression to describe ideas that were so vague or flexible they didn't make specific enough predictions to be falsified. The underlying idea is that a genuinely useful scientific theory must make specific and risky predictions that can be clearly and definitively right or wrong. If a theory is so flexible and adaptable it can accommodate practically any conceivable experimental result through ad hoc adjustments in its parameters, then it completely loses its explanatory and predictive power. Have you ever found yourself in a situation where an explanation sounds elegant and intellectually attractive but too good to be true? Where the beauty and sophistication of an idea might be masking a lack of real empirical substance? String theory's most serious critics genuinely worry that the international physics community might have collectively fallen in love with a mathematical mirage, something that appears beautiful and promising from afar, but reveals itself to be empty of verifiable physical content when examined closely with the experimental rigor that traditionally defines science. But string theory's defenders, many of them among the most respected and mathematically sophisticated theoretical physicists in the world, respond to these criticisms with equal passion and equally articulated arguments. They argue persuasively that physics history is replete with theories that seemed impossible to test when first proposed by visionary minds, but eventually found dramatic experimental confirmation through the development of new technologies and experimental methods. Einstein's general relativity, for example, was formulated in 1915 but was only tested experimentally in a convincing way decades later, when we developed instruments sensitive enough to detect the subtle effects it predicts. Furthermore, string theory defenders argue with considerable justification. The theory has already produced profound and unexpected mathematical insights in other areas of physics and pure mathematics, insights that probably wouldn't have been discovered otherwise. It led to important discoveries in number theory, differential geometry, algebraic topology, and even helped physicists better understand aspects of traditional quantum mechanics and field theory that had remained mysterious for decades. It's as if string theory were an extraordinarily powerful intellectual tool that, even if it doesn't directly and literally describe our specific physical reality, teaches us important and unexpected truths about the deep structure of nature, mathematics, and the relationship between them. Perhaps its true historical value lies not in being literally true as a final description of reality, but in dramatically expanding our collective imagination about what is mathematically possible, physically conceivable, and intellectually explorable. Although fundamental strings might be too small to be observed directly through any conceivable experimental means, there's something poetically appropriate and deeply satisfying in the fact that their consequences and implications might be potentially visible at the largest observable scales of the universe. It's as if nature, in its infinite wisdom and cosmic sense of humor, had hidden clues about its most intimate secrets in the most grandiose and spectacular phenomena we can observe with our most powerful telescopes and most sensitive detectors. Think of the cosmos as a giant and patient detective, where each distant galaxy shining in the darkness, each gravitational wave propagating through the fabric of space-time, each particle of cosmic background radiation carrying information about the universe's first moments, might be transporting encoded information about the fundamental structure of reality. And physicists specializing in string theory have become increasingly sophisticated and creative detectives, developing ingenious methods to search for these extremely subtle but potentially revealing clues. One of the most ardently sought and theoretically promising signatures are direct or indirect evidence of extra dimensions. If they really exist as string theory proposes, they should leave detectable footprints in the way gravity behaves at very small scales. Subtle but measurable alterations in gravitational force that could be detected by extraordinarily delicate and precise experiments. Imagine you're walking on a beach and see clear footprints in the wet sand. Even without directly seeing who made them, you can deduce important information about the person, their approximate size, weight, walking speed, direction of movement. Similarly, extra dimensions could leave characteristic and identifiable footprints in the way gravitational force operates and propagates. In our familiar three-dimensional world, gravity religiously obeys the mathematical law of the inverse square of distance. If you double the distance between two massive objects, the gravitational force between them decreases by a factor of exactly 4. This relationship has been verified experimentally with extraordinary precision at scales, ranging from terrestrial laboratories to entire planetary systems. But if genuine and accessible extra dimensions existed, gravity could leak into these dimensions at very small distances, fundamentally altering this familiar relationship and creating detectable deviations from Newton's law. Extremely delicate and technologically sophisticated experiments have attempted to measure gravitational force between objects separated by distances smaller than a millimeter, searching for any deviation from classical law that could indicate the presence of extra dimensions. It's an almost impossible task to accomplish, like trying to hear a delicate whisper amid a deafening symphony, or like trying to weigh a feather while a hurricane blows around. So far, gravity has behaved exactly as Einstein predicted and Newton before him established, but experiments continue becoming more sensitive each year, pushing the limits of experimental technology into previously unimaginable territories. There's also the systematic and international search for supersymmetry, an almost inevitable mathematical consequence of many versions of string theory that relates particles of different types through elegant mathematical transformations. Supersymmetry proposes that each known particle in the standard model of particle physics has a supersymmetric partner, shadow particles with complementary properties that we haven't discovered experimentally yet. But that should exist if supersymmetry is a real symmetry of nature. If these partner particles exist as theory predicts, the Large Hadron Collider, LHC in Switzerland, the most powerful experimental machine ever built by humanity, could eventually create them in high-energy collisions between protons accelerated to near light speed. The search for these supersymmetric particles is like a cosmic archaeological expedition, excavating in the subatomic ruins left by particle collisions to find fragments of more fundamental physics. Each collision at the LHC is like a small controlled Big Bang, recreating energy conditions that hadn't existed in the universe since its first moments, offering a window to physical processes that might reveal the deeper structure of reality. It's also like searching for echoes of a conversation that happened billions of years ago in the first moments of cosmic creation. String theory predicts that the primordial universe might have been filled with cosmic strings, enormous and energetic one-dimensional structures, fundamentally different from the microscopic strings that compose particles, but related to them through the theory's mathematics. These cosmic strings, if they existed during the universe's inflationary epoch, would have left subtle but characteristic marks in the cosmic background radiation. The residual glow of the Big Bang that uniformly permeates all space and carries encoded information about physical conditions in the first moments of cosmic existence. Increasingly sophisticated and sensitive telescopes methodically scan the night sky, mapping the tiny variations in cosmic background radiation temperature with constantly improving precision. It's a search that requires almost Zen-like patience and monastic dedication, analyzing trillions of data points, searching for specific statistical patterns that could reveal the signature of cosmic strings or other exotic primordial structures. Scientists look for small irregularities in radiation distribution, anomalies that could indicate that primordial spacetime was disturbed by objects or processes that don't exist in conventional physics. And there's something more promising and revolutionary: gravitational waves. These literal ripples in the very fabric of spacetime, predicted by Einstein more than a century ago, but detected directly for the first time only in 2015, have opened a completely new experimental window to the cosmos and to fundamental physics. LIGO detectors in the United States, Virgo in Europe, and other gravitational wave observatories around the world can detect spacetime distortions, smaller than 1,000th of a proton's diameter, a sensitivity so extraordinary it defies imagination. Some specific versions of string theory predict unique signatures that could be visible in these gravitational waves, characteristic vibration patterns, that would be produced by fundamental processes involving strings or extra dimensions. When black holes collide and merge, when neutron stars dance in decaying spirals, when spacetime itself oscillates like the surface of a lake disturbed by a cosmic stone, these events might carry information about physics at much smaller scales than anything accessible in terrestrial laboratories. Have you ever felt that particular and unmistakable excitement of being about to discover something important? That sensation of anticipation mixed with anxiety that accompanies moments of possible revelation? The international scientific community lives in perpetual state of this intellectual and emotional anticipation, knowing that the next astronomical observation, the next laboratory experiment, the next gravitational wave detection could reveal definitive evidence of a reality much richer, stranger, and more mathematically beautiful than anything we've ever imagined in our most ambitious dreams. Each passing day, each new datum collected, each refined analysis, potentially brings us closer to a transformative moment in human history. The moment when we'll discover whether we live in a universe of 3 spatial dimensions populated by point particles, or whether we inhabit a multidimensional cosmos where vibrating strings play the silent music of reality at scales that transcend our current capacity for direct perception. There are rare and precious moments when mathematics completely transcends its utilitarian function as a calculation tool and becomes something close to pure art. To poetry in the form of equations, to music composed in symbols and abstractions that speak directly to the human soul. String theory is absolutely replete with these moments of transcendent beauty, equations so elegant, so unexpectedly harmonious, so surprisingly beautiful in their internal structure, that they make the most experienced physicist pause in silent admiration, as if they were contemplating a Gothic cathedral or hearing a Bach fugue for the first time. Consider the deep and multiple symmetries that permeate the theory like veins of gold running through solid rock. Not just the supersymmetry we mentioned earlier, but even more abstract and mathematically sophisticated symmetries, complex geometric transformations that leave the fundamental equations completely unchanged, preserving their mathematical form even when viewed from radically different perspectives. It's like discovering that a painting remains perfectly beautiful even when observed from geometrically impossible angles, or that a musical composition maintains its fundamental harmony even when its notes are systematically transformed in ways that should destroy its structure, but miraculously preserve its aesthetic essence. One of these symmetries is known to physicists as T-duality, a mathematical relationship that suggests something almost mystical and philosophically disturbing, that a universe with very small extra Dimensions is mathematically equivalent and indistinguishable from a universe with very large extra dimensions. It's like discovering that a microscopic grain of sand and an immense ocean are, in some deep and non-intuitive way, the same thing viewed from different perspectives, or that the infinitely small and infinitely large are different faces of the same cosmic coin. Another equally fascinating symmetry is S-duality, which proposes that apparently completely different theories, with superficially distinct mathematics and apparently contradictory predictions, are actually different aspects of the same fundamental theory viewed through different conceptual lenses. Imagine the philosophical revelation of discovering that all human languages, with their unique grammars, distinct vocabularies, their apparently incompatible syntactic structures, are actually regional dialects of a single, primordial universal language from which all emerged and to which all can be translated with perfect fidelity. S-duality promises something conceptually similar for theoretical physics, the unification of apparently disparate theories into a single, more fundamental mathematical structure. But perhaps the most profound and philosophically revolutionary is the ADS-CFT correspondence, discovered by Argentine physicist Hermann de Sena in work that permanently changed the landscape of theoretical physics. This correspondence, expressed in mathematics of almost supernatural beauty, suggests that a complex quantum theory living on the boundary of a curved space can be completely equivalent to a gravitational theory operating in the interior of that space. It's like discovering that an apparently two-dimensional hologram contains all the information necessary to perfectly reconstruct a complex three-dimensional object, or that a shadow cast on the wall can, through adequate mathematics, reveal all details of the object that produces it. These mathematical discoveries raise profound and potentially disturbing philosophical questions about the fundamental nature of reality and knowledge. If apparently different theories are mathematically equivalent at their deepest cores, which one describes the true or most fundamental reality? Or perhaps the question itself is philosophically meaningless, that reality is more like a complex symphony that can be written in different musical notations, all equally valid and revealing, but none more true than the others? And this inevitably leads us to an even deeper and existentially significant question: where exactly does consciousness, your consciousness, my consciousness, the subjective experience of being a conscious observer in an apparently objective universe, fit into this cosmic picture of vibrating strings and hidden dimensions? If we're really made fundamentally of microscopic strings vibrating in specific patterns through dimensions we can barely imagine, if our most intimate thoughts are complex patterns of vibration in multidimensional spaces, what does this mean for our direct and unequivocal, subjective experience of conscious reality? You are conscious at this moment, you're reading these words, you're thinking, you exist as a center of subjective experience in an apparently external world. This consciousness is perhaps the most fundamental and indisputable fact of your existence. But how do patterns of vibration in abstract 10 or 11-dimensional spaces give rise to this intimate and apparently non-physical experience of consciousness, subjectivity, qualitative experience? It's a mystery that string theory, for all its impressive mathematical sophistication and unifying power, hasn't even begun to systematically address. Some philosophers of mind speculate that consciousness might be an emergent property, something that arises naturally when vibration patterns reach a sufficient level of complexity, self-organization, and functional integration. It's similar to the mysterious way millions of individual neurons in your brain, each following relatively simple biochemical rules, somehow collectively give rise to the extraordinary richness of conscious experience, to the feeling of being you. Other more radical thinkers suggest that consciousness might be even more fundamental, perhaps a basic and irreducible property of the universe, like mass, electric charge, or energy. In this panpsychist view, vibrating strings don't just give rise to familiar matter and energy, but also to different flavors or qualities of conscious experience that might permeate the cosmos and forms our current science doesn't even have adequate language to describe. It's an idea that's simultaneously dizzying and consoling, that each distant star shining in the darkness, each rocky planet silently orbiting, perhaps even each individual atom vibrating in its quantum state, might possess some rudimentary but genuine form of internal subjective experience. That the universe isn't merely a giant cosmic machine mechanically computing its own evolution through blind physical laws, but a conscious being of unimaginable complexity and sensitivity, dreaming about itself through billions of years of cosmic time. Have you ever wondered, in moments of deep reflection or silent meditation, if your thoughts are really just yours in the individual sense, or if they're part of a much larger pattern of cosmic consciousness? If we're really made of vibrating strings playing reality's music, perhaps we're not separate and isolated observers of the universe, but local and temporary ways by which the universe itself develops the capacity to become conscious of its own existence, to question its own nature, to contemplate its own beauty and mystery through eyes that are, ultimately, its own eyes. There's something profoundly and inherently human about our compulsive need to look toward the future and imagine possibilities, to dream of discoveries we haven't yet made, to anticipate revelations that might completely transform our understanding of reality. Where exactly will string theory take us in the coming decades? What extraordinary discoveries await the brilliant young physicists who today are just beginning their scientific journeys, studying at universities around the world, asking the first questions that might one day revolutionize our understanding of the cosmos? String theory's future unfolds simultaneously on several promising and challenging fronts. There's the continuous and increasingly sophisticated experimental search, each new generation of more powerful particle accelerators, each more sensitive telescope capable of seeing deeper into space and time, each more precise and comprehensive gravitational wave detector offers a precious new opportunity to find direct or indirect evidence of physics beyond the current standard model, evidence that could validate or refute specific aspects of string theory. The LHC in Switzerland, this modern cathedral of experimental science, continues colliding protons at increasingly higher energies with almost unimaginable precision, creating conditions that hadn't existed in the universe since its first instance. Systematically searching for supersymmetric particles, evidence of extra dimensions, or any deviation from well-established predictions of conventional physics. It's like patiently fishing in a cosmic ocean of possibilities, never knowing what kind of extraordinary and unexpected creature might bite the conceptual hook. What discovery might emerge from data collected in each high-energy collision? There are also fascinating and mathematically rich theoretical developments emerging on the intellectual horizon of fundamental physics. The ADS-CFT correspondence we mentioned earlier has proven incredibly fertile and surprisingly applicable, not just for theoretical fundamental physics, but for areas apparently completely unrelated like condensed matter physics, quantum information theory, and even for understanding complex systems in general. It's one of those rare mathematical discoveries that open doors to conceptual territories we didn't even know existed. Physicists have discovered, to their surprise and delight, that complex physical systems, from high-temperature superconductors operating in terrestrial laboratories to black holes evaporating through Hawking radiation, can be modeled, understood, and predicted using sophisticated mathematical tools originally developed for string theory. It's like discovering that the same mathematical language that perfectly describes musical composition also describes with equal elegance architecture, painting, dance, and poetry, a universality of application that suggests we're touching something truly fundamental about the structure of reality. But perhaps the most exciting and potentially revolutionary development is the gradual emergence of a deeper and more unified understanding of the mysterious relationship between information, entropy, gravity, and the nature of spacetime. String theory is contributing significantly to a conceptual revolution in our understanding of black holes, these exotic objects that represent the most extreme physics accessible to current observation, suggesting that they might be, in some mathematically precise but conceptually surprising way, giant quantum holograms. Imagine the philosophical discovery that all information contained in a black hole, every particle that ever fell through its event horizon, every bit of information that was ever swallowed by its relentless gravity, is somehow mathematically encoded on the two-dimensional surface of that horizon, as if the entire infinite library of information from the interior were written in compressed form on the two-dimensional external cover. It's like discovering that all the voluminous content of a multidimensional encyclopedia is perfectly preserved and accessible in the letters printed on its external cover. This idea has profound and potentially transformative implications not just for our understanding of specific black holes, but for our fundamental understanding of the nature of space, time, information, and reality. Perhaps our three-dimensional universe is itself a kind of giant cosmic hologram, a projection of fundamental information encoded on a distant and normally inaccessible boundary, a surface that exists in dimensions transcending our direct experience. And there are tantalizing whispers of something even more revolutionary and philosophically transformative. The possibility that string theory might eventually help us understand not just what the universe is in its physical structure, but why it exists in the first place. Why does something exist instead of nothing? Why do the laws of physics have the specific and elegant mathematical form they have? Why is mathematics created by human minds so extraordinarily effective at describing and predicting the behavior of a universe that existed billions of years before the evolution of human intelligence? These are questions that touch the most delicate frontier between empirical science and speculative philosophy, between verifiable knowledge and profound existential mystery. String theory might not have definitive and complete answers to these ultimate questions, but it's systematically equipping us with new conceptual tools, new mathematical languages, and new perspectives to approach these ancient enigmas that have fascinated and perplexed humanity since we developed the capacity to ask abstract questions about our own existence. The future is simultaneously exciting in its promise and humbling in its uncertainty. String theory might prove, in the coming decades, to be the long-sought key to definitive and unified understanding of the cosmos in all its aspects. Or it might prove to be a fascinating and mathematically fertile, but ultimately unproductive detour in humanity's long journey toward physical truth. But one thing seems certain and consoling. The intellectual journey itself, regardless of its final destination, has already permanently transformed our way of thinking about reality, space, time, matter, energy, consciousness, and our place in the great cosmic scheme. Have you ever considered that you might be living in a unique and privileged moment in human intellectual history? A moment when our species is potentially about to discover truths about the fundamental structure of reality that have remained completely hidden since the beginning of time? Or perhaps we're just in the first timid steps of an epic intellectual journey that will extend for centuries or millennia, an adventure of discovery that our descendants will continue long after our individual lives become historical memories. As our contemplative journey through the mysteries of string theory gradually approaches its natural end, it's appropriate to pause in silent reflection and carefully consider what we've learned, not just about fundamental physics and abstract mathematics, but about the broader human condition, about our relationship with knowledge and ignorance, and about our simultaneously humble and magnificent place in the great cosmic scheme unfolding around us and through us. String theory teaches us, above all and in a profoundly necessary way, intellectual and existential humility. It reminds us unequivocally that the reality we perceive directly through our limited senses, this familiar world of apparently solid objects, vibrant colors, tactile textures, immediate and tangible sensory experiences, might be only the shallowest and most superficial surface of something unimaginably deeper, stranger, richer, and more mathematically sophisticated than our everyday intuition could ever suggest. Think for a moment about how your fundamental perception of reality might have changed throughout this intimate conversation we've shared. When we began our conceptual exploration together, perhaps you thought of the universe as something relatively simple and directly comprehensible, a place of three spatial dimensions populated by solid objects obeying familiar and intuitive physical laws. Now, you've been gently invited to seriously consider the extraordinary possibility of extra dimensions rolled into geometries of transcendent complexity, of microscopic strings vibrating in cosmic harmonies that determine all the structure of reality, of parallel universes existing beyond our capacity for direct observation, of a mathematics of nature so deep and elegant it makes our best symphonies seem simple in comparison. It's a transformation of perspective similar to that which our ancestors experienced when they gradually discovered that Earth isn't the fixed center of the universe, that countless galaxies exist beyond our own Milky Way, that time and space are relative and malleable, that matter and energy are equivalent and interchangeable. Each generation of humanity discovers with surprise and sometimes discomfort that the universe is more vast, stranger, more counterintuitive, and more magnificently complex than the previous generation ever imagined in its most audacious speculations. String theory also teaches us profound lessons about the intrinsic limits of human knowledge and conscious experience. There are apparently fundamental boundaries to what we can directly observe, experimentally measure, or even conceptually imagine with our minds evolved to navigate in a world of medium scales. Our brains and sensory systems evolved over millions of years to survive and thrive in an environment of medium-sized objects, moving at moderate speeds, operating on timescales accessible to biological experience. When we try to transcend these limits to understand the very small, very large, very fast, very slow, or very strange, we quickly reach the limits of our natural intuition and must rely on mathematical abstractions that challenge our imagination. But here lies the extraordinary miracle of human mind and scientific enterprise, even operating far beyond the limits of our everyday intuition. Even exploring conceptual territories our senses will never be able to visit directly, we can still make genuine and meaningful progress. Through rigorous mathematics, systematic logic, disciplined scientific creativity, and international intellectual cooperation, we can explore realms of reality that completely transcend our direct sensory experience. It's as if we had developed a form of vision that transcends our physical eyes, a capacity for perception that goes far beyond our limited biological senses. This leads us to a profound reflection on the nature of scientific truth and human knowledge in general. Science isn't fundamentally about discovering absolute and final truths about reality, a quest that might be impossible in principle for finite minds in a potentially infinite universe. Instead, science is about building increasingly better, more precise, more comprehensive, and more useful models of reality, conceptual maps that help us navigate and understand the world around us with growing sophistication and effectiveness. String theory might or might not be true in the literal sense of direct correspondence with fundamental physical reality, but it has already proven its intellectual and cultural value by dramatically expanding our collective imagination about what is possible, by suggesting new creative ways to think about ancient and apparently intractable problems, by connecting areas of physics and mathematics that seemed completely separate and unrelated. Even if it's eventually replaced by more complete theories or abandoned in favor of radically different approaches, it will have served a crucial historical role in the continuous evolution of our collective understanding. There's also an important lesson about intellectual patience and scientific perseverance. String theory has been in active development for more than half a century, involving some of the brightest minds of our era, and we still don't have definitive and unquestionable experimental evidence of its fundamental validity. This could easily discourage researchers less dedicated or committed to the pursuit of truth. But the history of science is absolutely replete with theories that took decades or even centuries to be experimentally confirmed. Theories that seemed speculative or impossible to test when first proposed by scientific visionaries. Can you imagine the extraordinary personal dedication required to work on a theory that might not be experimentally validated during your own lifetime? It's almost an act of intellectual faith, not religious faith in the traditional sense, but deep faith in human capacity to eventually understand nature, no matter how profound its mysteries, no matter how many decades or centuries the journey might require. And finally, perhaps most importantly, string theory teaches us about beauty. Beauty in a sense that transcends traditional visual or auditory aesthetics. There's something profoundly and inherently beautiful in the idea that all the apparently chaotic complexity of the universe, from the rhythmic beating of your heart to the gravitational dance of distant galaxies, from the delicate blooming of a flower to the explosive birth of new stars, can emerge gracefully from something as elegantly simple as vibrating, strings playing mathematical harmonies in hidden dimensions. It's a beauty that transcends any direct sensory experience. It's the beauty of profound mathematical order, underlying conceptual unity, intellectual elegance that unifies apparent diversity into fundamental harmony. Perhaps it's this search for mathematical and conceptual beauty that really motivates the most creative and dedicated theoretical physicists. Not just the pragmatic desire to understand and control, but the deeper and almost spiritual desire to find harmony where others see only apparent chaos, to discover elegant simplicity where others see only bewildering complexity, to reveal the silent music that might be constantly playing at the heart of reality itself. And so we naturally arrive at the contemplative end of our evening journey through the deep and fascinating mysteries of string theory. But like every genuinely meaningful conversation about the cosmos and our relationship with it, our apparent end is just a new beginning in disguise, a warm invitation to even deeper, more intriguing, more fundamental questions about the nature of existence, consciousness, and reality. At this present moment, as you silently absorb everything we've explored together throughout this intellectual and imaginative journey, the universe continues its ancestral and majestic dance. Stars continue shining with their nuclear light, being born in nurseries of cosmic gas and dust and dying in spectacular explosions that seed space with heavy elements, all in cycles extending over billions of years of cosmic time. Galaxies continue moving away from each other in an accelerated expansion that began almost 14 billion years ago, carried by the mysterious dark energy that constitutes most of the universe but remains one of modern physics' greatest unknowns. And if string theory is correct in its most fundamental predictions, trillions of microscopic strings continue vibrating eternally in hidden dimensions, playing the silent and mathematically perfect music that might be reality's true score, the cosmic composition from which all existence emerges as a symphony of unimaginable complexity. But what fascinates me most deeply about this extraordinary theory, and about the entire human scientific adventure of which it's part, is how it simultaneously connects us to the infinitely small and infinitely large, revealing a fundamental continuity that permeates the entire scale of existence. Each individual atom in your body might be composed of vibrating strings that participate in the same universal cosmic symphony that governs the formation of entire galaxies, that governs the behavior of supermassive black holes, that determines space-time curvature on cosmological scales. You're not separate or isolated from the universe as an external observer. You're a local and temporary way by which the universe itself experiences itself, knows itself through conscious eyes, questions itself through a curious mind that is, ultimately, a natural product of its own fundamental laws. There's something profoundly consoling and spiritually comforting about this cosmic perspective, especially during those solitary nights, when we feel small and apparently insignificant before the impressive vastness of the observable universe. If we're made of the same fundamental substance as the most distant stars, if our individual consciousness is a local expression of the same cosmic creativity that continuously generates new universes, new dimensions, new possibilities of existence, then our presence here isn't a meaningless statistical accident, but a natural and perhaps inevitable consequence of nature's deepest and most elegant laws. We are ways by which the universe developed the extraordinary capacity to contemplate itself, to question itself, to seek understanding of its own nature through science, art, philosophy, and love. String theory also reminds us, in a simultaneously humbling and inspiring way, that living with profound mystery isn't a temporary failure of human knowledge that will eventually be corrected, but the natural and permanent condition of finite minds exploring a reality that might be infinitely rich and complex. Each genuine answer we find through rigorous scientific investigation inevitably generates 10 new subtler and more challenging questions. Each conceptual frontier we manage to cross through decades of theoretical and experimental work reveals even more vast and unexplored landscapes extending to horizons we can barely imagine. It's like climbing an intellectual mountain only to discover, from its apparently final peak, that there are entire mountain ranges of complexity and mystery extending in all directions beyond the horizon, each promising adventures of discovery that could occupy entire civilizations for millennia. And perhaps that's exactly how it should be. at least for creatures like us who find meaning and purpose in exploration, discovery, and continuous growth of understanding. A completely comprehensible reality, totally mapped and explained, would ultimately be an impoverished reality, a claustrophobic cosmos where there would be nothing left to discover, no mystery to explore, no frontier to transcend. Mystery isn't our intellectual enemy. It's our deepest and most lasting inspiration. It's what keeps us perpetually curious, intellectually humble, in constant mental and perhaps spiritual growth. Think of small children observing the night sky for the first time, their eyes shining with genuine curiosity, asking simple but profound questions that adults often forget to ask. Why do stars shine with their own light? What are they really made of? Are there other conscious beings out there looking back at us? What existed before the universe began? Why does anything exist instead of nothing? String theory invites us to recover and cultivate this fundamental childlike curiosity, but now, armed with the sophisticated tools of advanced mathematics, modern theoretical physics, and decades of precise experimental observations. In the coming decades of your life, you'll witness scientific discoveries and revelations about the nature of reality that today we can't even imagine in our most ambitious dreams. Perhaps we'll finally detect unmistakable experimental signatures of the extra dimensions predicted by string theory. Perhaps we'll find observational evidence of parallel universes through anomalies in cosmic background radiation or specific patterns in gravitational waves. Perhaps we'll develop revolutionary technologies based directly on string physics that transform our civilization in ways we still can't predict, perhaps ways to manipulate the very geometry of space-time, to access energy sources based on reality's multidimensional structure, to communicate through extra dimensions or even between parallel universes. Or perhaps string theory will eventually be replaced by something even more extraordinary and mathematically elegant. A theory that makes vibrating strings seem like simple and limited concepts in comparison. Science history repeatedly teaches us that reality has the persistent and wonderful habit of surpassing our imagination, of being richer, stranger, more beautiful, and more surprising than anything we can conceive in advance. But regardless of what the specific future holds for string theory and fundamental physics, you now carry with you a transformative new perspective on your own existence and on the nature of reality. You know, you might be literally made of mathematical music, harmonic vibrations in hidden dimensions existing beyond direct perception. You know, your everyday familiar reality might be just a small island of conscious experience, floating in an infinite ocean of multidimensional possibilities. You know that each genuine scientific answer is simultaneously an intellectual conquest and a newly opened door to even greater and deeper mysteries? And this brings us philosophically back to our contemplative beginning, that moment when you settled in comfortably for this intimate conversation, perhaps without fully knowing you would. Embark on a conceptual journey to the deepest foundations of known and imagined reality. You're still in the same physical place where we began, but your conscious mind has traveled conceptual distances that make light years seem like centimeters, that make the speed of light seem like a slow walking pace. Thank you for patiently accompanying me with an open mind in this exploration of the frontiers of human knowledge. Thank you for keeping your curiosity alive and active, for possibilities that challenge common sense and transcend everyday experience. Thank you for participating in humanity's great collective intellectual adventure of trying to understand our place in the cosmos, of questioning the fundamental nature of existence, of seeking meaning and pattern amid the apparently chaotic complexity of reality. Now, as you gradually prepare for nightly rest, you carry with you not just specific knowledge about string theory and its mathematical implications, but a renewed sense of wonder at reality and at the extraordinary adventure of being conscious in a universe so rich with mystery and possibility. Every breath you take, every rhythmic beat of your heart, every thought that gracefully flows in your mind, all of this might be direct expressions of a cosmic harmony deeper, more fundamental, and more beautiful than we ever dared imagine in our most visionary moments. String theory whispers to us the possibility that we live in a universe that is, in its most intimate essence, a mathematical work of art in constant creation, an infinite musical composition being played at scales ranging from the smallest to the largest, from the simplest to the most complex, from the most familiar to the most exotic. If this is true, then every moment of consciousness is an opportunity to participate in this cosmic symphony, to contribute our own unique note to the universal harmony, to be simultaneously audience and performers in the great musical work of existence. A final question for your deep and personal reflection. If we discovered tomorrow that string theory is completely true in all its most extraordinary aspects, that you are literally made of mathematical music vibrating in hidden dimensions, that infinite parallel universes coexist with ours, that reality is fundamentally stranger, richer, and more poetically beautiful than any work of science fiction ever imagined, how would this cosmic revelation change the way you live your daily life? How you relate to other conscious people, how you understand the meaning and purpose of your existence in this infinitely mysterious and mathematically elegant cosmos. What difference would it make to know that you are, simultaneously, an individual note in a universal symphony and a mode by which that symphony becomes conscious of its own transcendent beauty?